A mass of 10 kilograms is attached to a hanging spring and allowed to come to rest in its equilibrium position, stretching the mass 12 centimeters beyond its natural length. The mass is then pulled down an additional 5 centimeters and released from rest. Assuming no damping, find a formula for the position of the mass after t seconds. Make sure to clearly define your coordinate system. The mass m is given as 10, and we know from the previous example that the spring constant is K equals 817. And since there's no damping and no external forces are mentioned in the problem, we also know that the damping constant C equals 0 and the net external force F equals 0. So our equation of motion is just 10y double prime plus 817y equals 0. We're also told that the mass is pulled down 5 centimeters from equilibrium. Since I'm choosing down to be the positive direction, and to make sure our units work out correctly, we should always use newtons, meters, kilograms, and seconds for metric. The initial position is y of 0 equals 0.05 meters. The mass is released from rest, so the initial velocity is 0, and y prime of 0 equals 0. So to find the position of the mass after t seconds, we need to solve the initial value problem, 10y double prime plus 817y equals 0, y of 0 equals 0.05, and y prime of 0 equals 0. Since the equation is second-order linear, constant coefficient, homogeneous, we can solve it using its characteristic equation. 10r squared plus 817 equals 0. I'm switching to r now for my variable since k is already being used for spring constant and I don't want to add any confusion. The solutions to 10r squared plus 817 equals 0 are r equals plus or minus the square root of negative 817 over 10, which is approximately plus or minus 9.04 I. So the general solution is y equals c1 sine of 9.04 t plus c2 cosine of 9.04 t. Now we can apply the initial conditions to get our formula for position. Y of 0 equals 0.05, so 0.05 equals c1 sine of 0 plus c2 cosine of 0. So c2 equals 0.05. Then, since y prime equals 9.04 c1 cosine of 9.04 t minus 9.04 c2 sine of 9.04 t, and y prime of 0 equals 0, 0 equals 9.04 c1 cosine of 0 minus 9.40 c2 sine of 0. So 9.04 c1 equals 0, so c1 equals 0. So our formula for the position of the mass after t seconds is y equals 0.05 cosine of 9.04 t, where down is the positive direction.